Okay, so today we're going to be talking about checking error assumptions. So what are the assumptions for linear regression with respect to the error? What are the assumptions we make with respect to that epsilon? We assume constant variance, normality, and independence. So we're going to be talking about how we can check these assumptions. Today we're going to be focusing specifically on the constant variance assumption. So we can't observe the error itself. We know that is true, but what can we observe? Well, we can observe the residuals. I often write these as E. Your book writes them as epsilon hat, but we can observe these residuals. And so maybe we can use these to help us sort of think about whether these assumptions are met. And so it's important to know that the residuals are not exactly the same as the error. And why is that? Well, let's look at the equation real quick to get a little bit more of a feel. You've been working a lot with the residuals. You calculated the expected value of the residuals, and you've been kind of working with them in a lot of different ways. But just to sort of get an idea of what's happening. So we know that the residuals are equal to just y minus y hat. And so we also know that we can write this as I, the identity matrix, minus h, the hat matrix, times y. And that's just because if we multiply y times the identity matrix, we just get y, so that gets back this part. And then we know that y hat is equal to the hat matrix times y, because the hat matrix puts the hat on y. So I'm just pulling that out to write it like this. So the residuals are equal to I minus h times y. And so we can pull out, we know that y is equal to x beta plus epsilon. And so we can pull this out like this, so we have I minus h times x beta plus I minus h times epsilon. Which means, based on, we've shown this before, that if we take I minus h times x beta, we know that that is going to just cancel out. And so then we end up with just this I minus h times epsilon. And so this is going to be how we would estimate the residuals. They're estimated by I minus h times epsilon. And because the expectation of epsilon, or the expectation of our errors, is 0, then the expected value of this residual is also going to be 0. And what is the variance of E, or the variance of our residuals? Well, we can just take the variance of this quantity that we've just calculated, and so we can pull out the I minus h because it's constant. And remember that I minus h has that special feature that when you multiply it by itself, it just gives itself back. You get itself back. So when you pull it out, normally when you pull out a constant from a variance calculation, you square it, or you end up with that constant times the constant transpose. But in this case, because this particular value is idempotent, we don't end up having to do that. We just end up with one I minus h out front. And then we multiply that by the variance of epsilon, since that's the thing that's random in this equation, which we know is sigma squared. So the variance of the residuals is going to be equal to I minus h times sigma squared. And so this is not exactly the same as the error, but nevertheless, diagnostics can be applied to the residuals to help check some of the assumptions of the error. And so that's what we're going to be doing today. So the main way to check constant variance is via something known as the residuals versus fits plot. And you've probably seen this before, but what do you think would be on the x and y axis of a residuals versus fits plot? It's exactly what it sounds like. So the y-axis are going to be the residuals, and the x-axis is just going to be the fits. And so this is what that looks like. Here's an example. This is an example from a data set that I had shown in several lectures ago, where we were looking at the relationship between wing length and weight for some birds, for some sparrows on a particular island, on Kent Island. And so here on the x-axis, I have y hat. So those are my predicted values here. And on the y-axis, I have the residuals from this model. And so I look at kind of what this looks like, and this looks like kind of what I would like to see if I'm checking for constant variance. And so when you're checking for constant variance, basically you're checking that the bands that these points fall between are constant. And so you don't see things like the points fanning out. And you might argue that, there might be a little bit more variation kind of here at the beginning of the plot versus here at the end of the plot, which might be true. There's kind of maybe not enough sample to know for sure, but this looks relatively okay to me if I were trying to assess kind of what I would like to see in a residuals versus fits plot in terms of constant variance. I'm going to show a couple plots that don't look good so you can get a sense of kind of what that looks like. And then you're actually going to do an exercise where you look at a whole bunch of different plots to kind of get a better feel for this. So what are we looking for? We're looking for random variation above and below 0. And we're looking for no apparent patterns. And basically the width of the band of points is relatively constant. And so this last point is really what's getting at constant variance. Some of these patterns can be due to nonlinearity, which is another assumption that we'll be talking about, that this plot is actually also good for checking. So what do you think of this plot, if this were the plot we got for residuals versus fits plot? So this explicitly violates that constant variance assumption, and the way you can tell is because the band of points here, it's fanning out, or basically it's changing depending on your y hat value. And so the variance, or the kind of distance between the points when you have a small predicted value, that distance is small, but as your predicted value gets bigger, that variance between those points is getting bigger. And so this is an exact example of the constant variance assumption being violated. So this is what a bad residuals versus fits plot would look like. This is another bad residuals versus fits plot, and this one is bad not necessarily due to constant variance, but due to nonlinearity, which, as I mentioned, is another assumption of linear models, although not the one that we're necessarily checking right now, but it's something to look out for when you're looking at residual versus fits plot. And so you want basically the distribution of points above and below 0 to be the same, and make sure that there are no patterns there. And so this is a clear kind of pattern that makes this look nonlinear, and also the distribution of points, there's way more points above 0 than below 0 here. And here's an example that kind of violates both. This one looks a little bit nonlinear and also definitely is violating that non-constant variance. And so you can see that distribution of the points is really not constant above and below 0, but also we end up with this band here being really, over here the variance is small and over here the variance is quite large, and so it's definitely not a constant variance across the fitted values. And so in addition to looking at the residuals versus the fitted values, you also could look at the residuals versus predictors or other x variables on the x-axis, and you would want to make sure you had kind of constant variance in that setting as well. So how do we actually check this in R? Well, if we fit a model, so for example, here I'm fitting a linear model. I'm using the MT cars data. I'm predicting miles per gallon from the DISP variable. And I can take that model and I'm going to stick some aspects of it into a data frame so I can plot it. And so I'm going to pull out the residuals here using the resid function. And so that pulls out the residuals of the model. And I'm going to pull out the fitted values, or those y hat values, using the fitted function. And so I'm pulling these out and I'm sticking them in a data frame. And that's so that I can use the ggplot2 package to plot these values. And so I'm going to use ggplot. My data is going to be D because that's what I've called this data frame. And then I'm going to plot on the x-axis the fitted values, and on the y-axis those residuals. So I'm putting some points down, so that's what the geom point does. That plots the actual points. And then it's good practice to have a horizontal line at 0 rather, so that you kind of have that grounding line to be able to make sure that you're getting that nice distribution. And so because we expect the residuals to have a average value of 0, this is what that y-intercept at 0 is helpful for. And so this is what that looks like for this particular data set. It's a bit hard to know for sure kind of if this is, because this is a small sample, kind of what's going on here. I wouldn't be particularly alarmed if I saw something like this, although it does look like maybe there's some nonlinearity happening. And the variance, if we look at kind of the band of these points, you might be able to argue that maybe it's getting a little bit bigger as you move along that fitted along the x-axis. And so if this were my data, I think I probably would say it's okay. I would kind of hope that I had more observations. But, this is sort of, the one challenge with this is that checking constant variance really is a bit of an art form because it's all done via plots, and some of this, it's really, you need to kind of gain practice seeing what these plots look like before you can kind of get a good sense. And that's because while there are formal tests that could maybe try to tell you if there is constant variance, they're only going to be violated if you basically have a large enough sample to be able to violate or to be able to kind of test that hypothesis. And the times when it's going to be the hardest to kind of know for sure when you have a small sample. And so formal tests for a lot of these assumptions are really not recommended because often all they tell us is that we're just not powered or we just don't have a large enough sample to kind of know for sure that our data doesn't meet this assumption. And of course, as you know that, the absence of evidence is not the same thing as the evidence of absence. And so just because we don't end up rejecting some null hypothesis about whether or not we have constant variance, that doesn't mean that we indeed do have constant variance. It just means that we might not have enough data to tell us for sure that we don't. So we don't often do formal testing. We really just look at these plots. And that's why I'm going to be showing you basically how to generate some of this data so that you can get a feel for what these plots look like to kind of get a better sense of good and bad plots by looking at a lot of them, because that's really the best way to do this as statisticians. We just get good practice because we look at these a lot. All right, so I'm going to show you how you can generate this data in R so that you can actually sort of get some feel for what these plots look like. And I think I'm going to show you how to generate a whole bunch of them so you can see kind of a whole bunch of good and bad plots, because that's basically the best way to get a handle on this and basically to get good practice at reading these graphs. And so what I'm doing here is I've set my sample size to 50, so I'm going to be plotting data sets that have 50 observations. And I've set my fitted values here. I'm just randomly sampling from a uniform distribution. So this R unif will randomly generate 50 uniform observations. And it's going to be 50 because I've set n equal to 50, and so that's going to be the main parameter. So this just randomly generates 50 observations. And so for my good data, I'm just going to set my fitted values to the fitted value that I've picked here. And then my residuals, I'm going to just set to be equal to be a random normal with the R norm. So R norm is a function that will generate random normal variables, and by default, the mean will be 0 and the standard deviation will be 1. And so this is going to generate the exact type of residuals that we'd like. And so best case scenario, our residuals are normally distributed with a mean of 0 and a constant variance, which in this case, the variance will be constant because they're gonna have a standard deviation of 1, and so therefore the variance will also be 1. So this is going to be good data. When I plot this, this will give you an idea for kind of what a good data set would look like. This is an example of some really bad non-constant variance, and so my fitted values are going to be the same, those ones I generated from this random uniform. But now my residuals, I'm still going to pull from a random normal distribution, but I'm actually going to multiply the fitted values by that, and that's going to give me a very bad non-constant variance plot. So if I plotted the residuals versus fits on this data frame, I'd expect it to look pretty bad. And then this will generate some mildly bad non-constant variance. And so instead of multiplying by the fit, we're going to multiply by the square root of the fit. And so it's going to have non-constant variance, but it won't be quite as bad as what we would see in this really bad version. And then finally, I have an example to show you what it could look like if you have nonlinear data. And so I've essentially multiplied by this nonlinear function. Your residuals are multiplied by this nonlinear function. So now you'll see this nonlinear relationship between your fitted values and your residuals. And so down here, what I'm doing is I'm just using the rbind function, which will bind the rows together of these 4 data frames that we've just created. So we end up with just one big data frame that we can then plot. And that big data frame is going to be called D. And so D is going to have 200 observations because each of these 4 data frames, each of these 4 small data frames has 50 observations because we've generated 50 random variables in each case. And so when we bind them together, we're basically just concatenating these 4 data frames together so that they kind of smush together and we end up with 200 observations total, 50 for the good, 50 for the really bad non-constant variance, 50 for the mildly bad, and 50 for the bad nonlinear. So then we can plot this relationship here. We can do that residual versus fits plot that we're used to seeing. And we can see, so to do that, I'm using the ggplot function. D is my big data set that contains all of the variables. X is going to be the fitted values. Y is going to be the residuals. Geom point, and I still use the geom H line to stick that 0 line at that point so we can sort of anchor our analysis. And then this facet underscore grid, what that's going to do is it's going to basically create a facet for each of my 4 conditions. And so I have this variable type. If you remember here, I've set this type equals good, type equals really bad, type equals mildly bad, and type equals bad nonlinear. And so what I'm doing is I'm faceting this plot by type so that it plots it separately for each of those types. And so we can see kind of what the good looks like, what the really bad looks like, what the kind of bad looks like, and what the nonlinear looks like. Although to me, that nonlinear one really doesn't look that bad in this particular poll. So it's going to just depend a little bit on kind of, it's why we're doing this multiple times so you can sort of see what it looks like across multiple different scenarios. Okay, so if I wanted to look, for example, at a bunch of good plots, just to get a feel for what good plots look like, I could stick this into a function. And so what I've done here is I've created a function called good that takes 2 arguments, I and n. And so I'm fitting that r unif n here, and I'm going to do my data frame. I'm going to plug that fitted value in. I'm going to calculate my residual, the same that I calculated in the data frame that I had showed you before. And I've just added one additional variable to this data frame, run, which I'm going to set to I, just so I can keep track of which run this is. So if I run this function one time, it'll generate 50 variables. If I set I to 1, run will just be 1. And those 50 variables, those 50 observations rather, with 2 variables, those 50 observations are going to kind of follow a nice relationship between my residuals and my fits where it'll look like what I want. And if I plotted that, I would get kind of a good plot to give you an idea for what a good plot looks like. So I'm going to use this per function, or this map underscore df function from the per package, which basically iterates across this function. So it runs this function, in this case, 9 times. And then it binds the rows of that function together so that we end up with one data frame that has the fit, the residuals, and the runs for each of these. So I end up with this big data frame called D. And so then I can plug that big data frame into the ggplot function, and I can have my x-axis be my fit, my y-axis be my residuals. I'm still using the same geom point and geom H line. And now, instead of using facet grid, I'm going to use facet wrap so that it'll wrap those facets kind of around in a kind of insensible way. And I want those to be based on the run, so I can just look at across 9 different runs what good plots look like. And so this kind of gives me some idea for what if I were to be seeing some good data, kind of what I would expect to see. And so what I want you to do now is I want you to use the code that I've provided in the previous slides. And I want you to, instead of generating good plots, I want you to generate multiple bad plots that have non-constant variance. And I want you to do it kind of in both the mild non-constant variance and the really bad non-constant variance, and then maybe generate a whole bunch of plots that look at the nonlinearity as well. And then I want you to write up a little bit what they look like, so you can sort of get a sense for what you're looking for when you're looking at these residuals versus fits plots. So go ahead and work on that.